Hey there! Welcome to our machine learning crash course, where we're going to make machine learning finally click for you. No PhD required. Forget those boring algorithm lectures that put you to sleep. This isn't just another technical course. This is your complete guide to understanding how machines actually think and learn. I know, AI can sound scary and maybe a little overhyped too. But here's the thing. You're already using machine learning every single day, even if you don't realize it. Spotify somehow knows you're heartbroken before your best friend does, creating the perfect sad playlist. Your phone magically sorts photos of your dog into one album and your baby cousin into another. Your smart alarm clock rings at 6:45 instead of 7 a.m. because it learned there's rain and traffic, even though you never told it anything. That's not random, that's not magic, that's machine learning, quietly working behind the scenes, making your life better. By the end of this course, machine learning won't feel like some mysterious black box. It'll feel like watching your mom learn your favorite foods over the years, observing, remembering, and surprising you with exactly what you need. Except instead of recipes, we're building digital brains, layer by layer. We're going to cover every major machine learning algorithm, but we'll do it in a way that actually sticks. With stories, analogies, and real-world examples that'll make you say, "Oh, that's how Netflix knows what I want to watch." Ready to code the secret language of intelligent machines? Let's dive in. Think about how you taught a kid to ride a bicycle. You didn't hand them a 100-page manual with every possible rule. You didn't say, if the bike tilts 15 degrees left, adjust your weight 3.7 degrees right. Instead, you let them try, fall, adjust, learn, and try again. That's exactly how humans learn, through experience, trial, and error. And here's the beautiful part. That's exactly how machines learn too. Traditional programming is like writing a recipe. You give the computer step-by-step instructions. If this happens, do that. If you see this pattern, take this action. But what happens when the problem is too complex for simple rules? Machine learning flips this completely. Instead of giving machines rules, we give them examples and let them figure out the patterns themselves. We show them thousands of photos labeled cat and dog, and they discover what makes a cat different from a dog, without us ever explaining whiskers or barks. Technically speaking, machine learning is a subset of artificial intelligence that trains systems to learn patterns in data and make predictions without being explicitly programmed for every possible scenario. Here's the mathematical heart of it. We want to learn a function, let's call it f, where f takes some input, x, and produces output y. So, f of x equals y. The input x might be an email's text, and y might be spam, or not spam. Or x could be a photo and y could be a cat or a dog. The magic happens when the machine builds a model that gets better over time by minimizing its mistakes, what we call loss, using optimization algorithms. Let me show you why this matters with a real example. Say you want to build a spam detector. You could try writing rules. If the subject includes free money, mark it as spam. If the sender ends in .ru, probably spam. But spammers get smarter. They start writing, "Congratulations! Claim your prize with just one click." Now, your rules break completely. So, instead of writing 500 rules that'll be outdated next week, you show the machine 10,000 examples, each of spam and legitimate emails. It starts noticing patterns. Spam emails use the words like urgent, win, click here. Real emails have newsletters, meeting invites, actual conversations. The machine builds its own rules based on real data, just like how you learn to recognize sarcasm from tone and context, not from a textbook definition. That's the power shift from programming to learning. Instead of us telling machines what to think, we show them examples and let them discover the patterns themselves. Let's play a game that'll show you exactly why machine learning became necessary. You want your computer to tell cats from dogs in photos. Sounds simple, right? Let's try the old-fashioned programming approach. Rule number 1. If the animal has pointy ears and whiskers, it's a cat. Rule number 2. If it has floppy ears and its tongue is hanging out, it's a dog. Seems reasonable, but wait. What happens when the cat is mid-yawn and looks like it has no whiskers? What about dogs with pointy ears? What if the photo is taken from a weird angle? What about lighting that makes their whiskers more invisible? You need thousands of rules to handle every possible scenario, and even then, you'd miss edge cases that break everything. This is where machine learning comes to the rescue. Instead of writing impossible rules, you gather 20,000 labeled photos, 10,000 cats, 10,000 dogs. You show them all to the machine and say, figure it out. The machine starts analyzing pixels, finding patterns you never would have thought of. Maybe cats have a specific texture in their fur that shows up in pixel intensity patterns. Maybe dogs have a particular way their ears cast shadows. Or maybe there are subtle color distributions that consistently distinguish the two animals. The machine discovers features that humans might completely miss. And it does this automatically, without us having to think of every possible rule. This isn't just programming anymore. This is learning. This is pattern recognition at a level that surpasses what we could manually code. And here's the key insight. The machine doesn't just memorize the 20,000 photos. It learns the underlying patterns. So when you show it photo number 20,001, a cat it's never seen before, it can correctly identify it as a cat. This fundamental shift from explicit rule writing to pattern discovery is what makes machine learning so powerful. It's why your phone can recognize your face even when you're wearing sunglasses, why translation apps work across hundreds of languages, and why recommendation systems know what you want to watch next. Now, let's talk about supervised learning. Imagine you're the coach, and the machine is your rookie player. Your job is to train this rookie using tons of examples where you already know the right answers. This is what we call labeled data. It's like having an answer key for every practice problem. You show the machine a picture and say, this is a dog. Then another picture, this is not a dog. You show it traffic data and say, this route takes 25 minutes on a rainy Tuesday morning. This other route takes 15 minutes. Over time, just like a good student, the machine doesn't just memorize these examples. It starts seeing patterns and learning the underlying rules. Think of it like teaching a child about weather and travel time. You might say, hey, when it rains, everything moves slower. Pretty soon, they stop asking how long the trip will take when it's raining. They just know. Technically speaking, supervised learning trains algorithms using labeled data sets, allowing them to become more accurate over time. This process is beautifully iterative. The algorithm makes a prediction, gets compared to the correct answer, and adjusts itself based on the error. Then it tries again and again and again. This supervised approach is incredibly powerful because it's grounded in real answers. With enough quality training, your machine can learn to predict how long your commute will take based on weather and time of day. It can determine whether a social media post violates community guidelines. It can flag fraudulent credit card transactions in real time. But here's the thing. Not every problem needs the same kind of brain. Sometimes you want a straight-line thinker for simple relationships. Sometimes you need a rule-making detective for complex decisions. Sometimes you want a system that acts like a pattern recognition master. Over the next several minutes, we're going to explore the most powerful supervised learning algorithms one by one. Think of it as building your toolbox. Want to predict a number, like house prices or stock values? Linear regression is your tool. Want to classify things into categories? Decision trees will be your friend. Want serious predictive power? Random forests and support vector machines are waiting for you. Each algorithm has its specialty, its sweet spot, its perfect use case. Let's start with the most honest, straightforward algorithm in machine learning: linear regression. Let's meet the OG of machine learning, linear regression. This is the most honest algorithm you'll ever encounter, and here's why. Imagine a city full of street performers. Every day they set up different neighborhoods. Some days it's sunny, some days it rains. Sometimes there's a festival happening. Sometimes the streets are empty. Each day, different amounts of money land in their tip jar. Now, you want to predict how much tip money they'll make before they even tune their first guitar string. So, you start gathering data: day of the week, weather conditions, crowd size, time of day, and most importantly, how much money they actually made. The question then becomes, can you find a mathematical relationship between all these input factors and the tip amount? That's exactly what linear regression does. It finds straight-line relationships between one or more inputs and a continuous numerical output. Here's the mathematical foundation. Linear regression assumes your output, y, is a linear combination of your inputs. The formula looks like this. Y hat equals W1 times X1 plus W2 times X2 plus W3 times X3, and so on, plus B. Let me break this down. Each X represents an input feature. Maybe X1 is crowd size, X2 is weather rating, X3 is time of day. Each W is a weight that shows how strongly that factor affects the outcome. And B is the bias. Think of it as the base prediction, even without any specific conditions. The algorithm learns these weights by minimizing that error, that gap between its guesses and real-life results. It's literally like drawing the best fitting line through all your data points. So the algorithm might discover, for every 10 additional people in the crowd, tips go up by $3. Rain decreases tips by $5. Evening performances earn $2 more than a morning one. Linear regression shines when relationships are predictable and stable. It's perfect for estimating delivery times, predicting sales based on advertising spend, or forecasting energy consumption based on temperature. But here's its limitation. This algorithm assumes life follows a straight line. If your delivery drone gets hit by unexpected wind, stops for traffic that doesn't appear in your data, or faces random delays that don't follow patterns, that beautiful straight line starts wobbling. You should use linear regression when you need simple, explainable predictions, when your data shows clear linear trends, and when you're predicting numbers, not categories. Avoid it when the relationships are curved or chaotic, when you have too many complex factors interacting in non-linear ways, or when you're working with text, images, or categorical data. Linear regression is your reliable, transparent friend in the machine learning world. It tells you exactly how it makes decisions, and when it's appropriate for your problem, it works beautifully. Let me show you linear regression solving a real business problem that you can immediately relate to. You're launching a drone delivery startup. Think Amazon Prime, but with flying robots. Your customers want one thing: accurate delivery time estimates before they place their order. So you start collecting real data from your test flights. 2-kilometer delivery, 5 minutes. 5-kilometer delivery, 13 minutes. 10-kilometer delivery, 28 minutes. When you plot this data, you see a roughly linear relationship. Distance goes up, time goes up, pretty predictably. But distance alone isn't the whole story. You also track weather conditions, clear skies, rain, wind, and package weight ranging from half a kilogram to 5 kilograms. Now, linear regression gets to work. It discovers the underlying mathematical relationship. Base time, 3 minutes for drone startup and landing. Distance factor, 2.5 minutes per kilometer. Weather penalty, 30% extra time in rain, 50% extra in high wind. And your weight factor, 10 seconds additional per 100 grams above 1 kilogram. So when someone orders from 7 kilometers away on a rainy day with a 2-kilogram package, your model calculates 3 minutes base plus 17.5 minutes for distance plus 30% weather penalty plus 1 minute for weight, total estimate, 27 minutes. This isn't just academic theory. This is real business value. Your customers get accurate expectations, your operations team can plan efficiently, and you build competitive advantage through reliable service promises. The beauty of linear regression is its transparency. You can explain to your business stakeholders exactly why delivery times change. Rain adds 30% to delivery time because drones fly more cautiously in poor weather conditions. But remember the assumptions. Linear regression works here because the relationships are stable and predictable. Drone speed is consistently affected by wind. Distance always matters in a linear way. Weather impacts are proportional. If your delivery system involved unpredictable variables, like drones that had to navigate through flocks of birds, or weather that changed randomly mid-flight, linear regression would struggle. Here's the key insight. Linear regression excels with predictable, stable relationships, but struggles with chaos or complex interactions. When your problem involves clear cause and effect relationships that follow straight-line logic, linear regression is often your best starting point. Next, we're moving from predicting numbers to making yes or no decisions. That's where logistic regression comes in, turning straight lines into probability curves. While linear regression predicts how much, logistic regression answers yes or no, but with a confidence score that makes all the difference. Picture this. You're training the world's smartest club bouncer. His job isn't to guess how tall someone is or estimate their age. He has one crucial decision. Should this person get in? Yes or no? Over the past month, you've shown him 1,000 past guests. For each person, you noted what time they arrived, how they were dressed, whether they were on the VIP list, their age, group size, and whether they caused any drama inside. Most importantly, you told him the final decision, admitted or denied. Now, here's where it gets interesting. This bouncer doesn't just make black and white decisions. When someone walks up at 10:52 p.m. wearing a hoodie, he doesn't just say denied. He says there's a 75% chance this person will cause problems. Since that's above my 50% threshold, I'm denying entry. That percentage, that confidence score, comes from logistic regression's secret weapon, the sigmoid curve. Here's how the math works. Logistic regression starts with the same linear combination as before. W1 times x1 plus W2 times x2 plus the bias. But instead of giving you that raw number, it squashes it through a special S-shaped curve called the sigmoid function. The formula is y hat equals 1 divided by 1 plus e to the negative z, where z is that linear combination we calculated. This sigmoid curve has a magical property. No matter what numbers you put in, the output is always between 0 and 1. Perfect for probabilities. So the bouncer's brain works like this. Well-dressed VIP arriving at 9 p.m. with one friend. The linear combination gives me plus 2.3, which the sigmoid converts to a 91% probability of being a good guest. They're in. Large group in hoodies arriving at midnight, that gives me a negative 1.8, which becomes 14% probability of being good guests. That's below my 50% threshold, so they're out. The beauty is in the confidence. Unlike a simple yes or no rule, logistic regression tells you how sure it is. This matters enormously in real applications. Let's take a look at a medical diagnosis system saying 75% chance of disease leads to different actions than 25%. A fraud detection system flagging a transaction with 95% confidence gets immediate action, while a 55% confidence score might just get extra monitoring. Use logistic regression when you need binary decisions with confidence scores, when you want probabilities rather than just classifications, and when your data has relatively clear boundaries between classes. It's perfect for email spam detection, medical diagnosis, loan approval, and any situation where you need to make a yes or no decision based by statistical confidence. Let me show you logistic regression solving a problem that's probably happening in your home right now. Imagine you have a smart thermostat that needs to make a decision every single minute. Should I turn the heat on right now or not? This isn't about predicting the exact temperature. That would be regression. This is a binary classification problem, heat on or heat off. Your thermostat considers multiple input features: current temperature, time of day, whether anyone's home based on motion sensors, humidity levels, outside weather conditions, and your historical preferences from months of data. During the learning phase, the thermostat observed thousands of situations, the environmental conditions at each moment, whether it turned the heat on, and most importantly, whether you seem satisfied with that decision based on your manual adjustments. Now, instead of rigid rules like turn on heat when temperature drops below 68 degrees, your smart thermostat uses logistic regression to make nuanced decisions. At 6 p.m. on a Tuesday, temperature is 67 degrees. Someone just came home. Humidity is normal, and it's cold outside. The algorithm calculates based on all these factors, there's a 92% probability the user wants heat right now. Since that's above the decision threshold, heat turns on. But at 2 p.m., when nobody's home, even if the temperature is 66 degrees, the model might calculate only 15% probability that heat is needed. Energy saved. The genius is in the probability thinking. Instead of binary rules that can't handle edge cases, logistic regression provides confidence-based decisions that adapt to complex, real-world situations. This probabilistic approach creates several business benefits: energy efficiency through smarter heating decisions, user comfort through proactive temperature management, and personalization as the system learns individual family preferences over time. The math behind this decision uses the same sigmoid function we discussed. All of those input features get combined with learned weights. Maybe someone just came home has a weight of 1.5, while nighttime hours has a weight of negative 0.8. Then squeeze through the S-curve to produce a probability. But logistical regression has its limitations as well. It assumes relationships between features and outcomes are relatively linear when transformed through the sigmoid. If your heating preferences depend on complex interactions, like only heat the house on weekdays when it's below 65 degrees and someone's been home for more than 30 minutes, unless it's a holiday, simple logistic regression will struggle. That's when you need algorithms that can handle more complex decision trees and rules. Which brings us perfectly to our next algorithm: decision trees, the detectives of machine learning. Meet the airport security dog. Let's call him Max. Max has one of the most important jobs in the airport, detecting prohibited food items in luggage. But Max doesn't make just one big decision. He makes a series of small, logical decisions that builds up to his final conclusion. His thought process goes something like this: do I smell something unusual? If no, move on to the next bag. If yes, is it food related? If not, ignore it. If it is food, is it meat or dairy? Different risk levels. Is it raw or cooked? Raw meat is higher risk. Is it from a country with import restrictions? That matters for the final decision. Should I alert my human partner? Final decision based on all previous answers. Each question branches into new questions, like limbs on a tree, until Max reaches his final decision: bark or don't bark. This is exactly how decision trees work in machine learning. They break complex problems down into a simple series of yes or no questions, with each answer leading to more specific questions until they reach a final prediction. But here, where it gets mathematically beautiful, the tree doesn't just ask random question. It chooses each question to maximize information gain, which is measured using something called entropy. Think of entropy as messiness. If you have a pile of emails where half are spam and half are legitimate, that's high entropy, completely mixed up. If you have a pile where 95% are spam and 5% are legitimate, that's low entropy, much more organized. Information gain measures how much a question reduces this messiness. The mathematical formula is information gain equals the entropy of the parent group minus the weighted average entropy of the child group after you split them. Let me show you how this works with a real example. You have 1,000 emails, 500 spam, 500 legitimate. That's maximum messiness, entropy of 1.0. Now you ask, does the subject line contain the word urgent? That splits your emails into two groups. Group A, 480 spam emails plus 20 legitimate emails. Group B, 20 spam emails plus 480 legitimate emails. Suddenly, both groups are much more organized, much less messy. The information gained from asking this single question is huge. You've gone from total confusion to pretty clear classification. But if you asked, is the email sent on a Tuesday, and got Group A, 250 spam, 240 legitimate, and Group B, 250 spam, and 260 legitimate, that question provides almost no informational gain. Both groups are still mixed up. Decision trees automatically find the questions that provide maximum information gain at each step, building the most efficient path to create accurate predictions. The transparency is incredible. Unlike other algorithms that work like black boxes, decision trees show you exactly why they made each decision. You can trace the path. This email was classified as spam because it contained urgent in the subject, came from an unknown domain, and had more than 3 exclamation points. Let me walk you through exactly how a decision tree builds itself, using our email spam detection example. We start with 1,000 emails sitting in one big messy pile. 500 spam, 500 legitimate. The entropy, our measure of messiness, is at a maximum 1.0. We're completely uncertain about any individual email. Now, the algorithm evaluates every possible question it could ask. It looks at every feature: sender, domain, subject line words, message length, time sent, everything. For each potential question, it calculates, if I split the data using this question, how much will I reduce the uncertainty? Let's say it tests the question, does the subject contain urgent? This creates 2 branches. Branch 1, 480 spam, plus 20 legitimate emails. Very high spam probability. And branch 2, 20 spam, plus 480 legitimate emails. Very high legitimate probability. The information gain calculation shows this equation reduces entropy from 1.0 to about 0.28. That's excellent. We've gained 0.72 bits of information. But what if it is tested? Is the sender domain exactly gmail.com? This might create a branch 1 of 200 spam and 300 legitimate, and branch 2 of 300 spam and 200 legitimate. Much less clean separation, much lower information gain. The algorithm chooses the question with the highest information gain. In this case, does the subject contain urgent? Now, we have 2 branches, but we're not done. The algorithm looks at each branch separately and asks, what's the best question to ask about the emails in this branch? From the urgent branch, mostly spam, maybe the best next question is, does the sender end in .biz? For the no urgent branch, mostly legitimate, maybe it's, does the message contain a calendar invite? This process continues recursively. Each branch gets split further based on the question that provides the most information gain for that specific subset of data. The tree stops growing when it reaches certain stopping criteria. All emails in a branch have the same label, pure leaf node. We've reached a maximum depth to prevent overfitting. We have fewer than a minimum number of emails in each branch. Further splitting doesn't improve information gain significantly. The result is a tree where each path from root to leaf represents a specific combination of characteristics that lead to a prediction. For a new email, we simply follow the path contains urgent. Yes. Sender ends in .biz. Yes. More than 5 exclamation points? Yes. Prediction? 94% probability of spam. This transparency makes decision trees incredibly valuable for applications where you need to explain your reasoning. Medical diagnosis, loan approval, and legal decisions. But single trees have a weakness. They can memorize training data too specifically, creating overly complex rules that don't generalize well. That's where our next algorithm comes in, random forest, which fixes this by including not one tree, but an entire forest of different trees that vote on the final decision. A single decision tree is like having one detective solve a complex case. But what happens when that detective has biases, makes errors, or focuses too much on irrelevant details? Now, imagine this instead. You assemble 100 different detectives. Each detective gets a slightly different view of the evidence. Some see witness statements, others don't. Some focus on physical evidence, others on timeline analysis. Each detective builds their own theory of the case using their own unique perspective. Then, instead of relying on just one opinion, you let all 100 detectives vote on the final verdict. This majority decision becomes your conclusion. That's exactly how random forest works. Instead of building one decision tree that might overfit or miss important patterns, random forest builds hundreds of trees, each with a slightly different perspective, then combines their predictions. Here's the mathematical beauty behind this approach. Each tree is trained on a random sample of your data. That is called bootstrap sampling or bagging. So, tree 1 might see samples 1, 3, 5, 7, 3, 9, and 1 from your dataset. Notice some samples appear multiple times, others not at all. Tree 2 gets a completely different random sample, 2, 4, 6, 8, 4, 2, and 10. But that's not the only source of randomness. At each decision point in each tree, instead of considering all possible features, each tree only looks at a random subset. Say, if you have 20 features total, each split might only consider 4 or 5 randomly chosen features. This randomness is the secret sauce. It ensures that your trees are diverse, that not all making the same mistakes or focusing on the same patterns. For classification problems, the final prediction is the majority vote of all trees. For regression problems, it's the average of all the trees' predictions. This approach solves a fundamental problem in machine learning called the bias-variance trade-off. Individual decision trees have low bias. They can learn complex patterns, but high variance, meaning they're unstable and change dramatically with small changes in training data. Random forest keeps the low bias, but dramatically reduces variance by averaging over many models. It's like the difference between asking one highly opinionated person versus surveying 100 people with diverse perspectives. There's even a built-in validation system, since each tree only uses about 2/3 of the data for training. It can be tested on the remaining 1/3. This gives you a free accuracy estimate called the out-of-bag error, without needing a separate validation set. Random forest also provides feature importance rankings. If a feature is useful for making accurate predictions, it will be chosen from splits across many trees. Features that appear frequently in important splits get higher importance scores. This algorithm excels with tabular data that has mixed data types. Some numerical features like age and income, some categorical features like job, title, and city. It requires minimal data pre-processing, handles missing values reasonably well, and provides robust predictions that rarely overfit dramatically. However, random forest trades some interpretability for accuracy. While you can get feature importance scores, you lose the simple if-then logic path that makes single decision trees so easy to explain. Think of random forest as your go-to algorithm when you want strong predictive performance without spending weeks tuning hyperparameters. It's the reliable workhorse of machine learning competitions and real-world applications. Now, let's meet the perfectionist of machine learning algorithms, support vector machines, or SVM. This algorithm doesn't just want to separate different classes. It wants to find the most confident, most robust separation possible. Picture an exclusive nightclub with two very different crowds gathering outside. On one side, you have VIPs arriving in luxury cars, wearing designer clothes with names on the guest list. On the other side, you have the general public, in casual attire, hoping to get in. Most algorithms would just draw any line that separates these groups, but SVM is like the most meticulous bouncer you've ever seen. It doesn't just want a line that separates VIPs from regular guests. It wants that line to give the maximum possible space between the two groups. This isn't just perfectionism for its own sake. The maximum margin approach makes the boundary much more robust. If a few people move around, if someone's outfit is ambiguous, if the lighting changes how people appear, that wide margin means the boundary is less likely to make mistakes. The mathematical foundation is elegant. SVM finds the hyperplane, which is just a fancy word for a decision boundary. That maximizes the distance to the nearest data points from each class. These nearest points are called support vectors, and they're the only points that actually matter for defining the boundary. Here's the key insight. SVM only cares about the most challenging examples, the ones closest to the decision boundary. All the obvious cases get ignored. It's like a teacher who focuses entirely on the students who are right on the borderline between passing and failing. because those are the cases that define where you draw the line. For linearly separable data, SVM solves an optimization problem. Minimize the norm of the weight vector, subject to the constraint that all training points are correctly classified with at least unit margin. But real-world data is messy. Classes often overlap. That's where SVM introduces slack variables, a mathematical way of saying, it's okay if a few points are misclassified as long as we don't sacrifice the overall margin quality. And here's where SVM gets really clever, the kernel trick. When data isn't linearly separable in its current space, SVM can project it into a higher dimensional space where clean separation becomes possible. I know, but think of it like this. Imagine you're trying to separate cats and dogs based on just weight and height. The class might overlap significantly in this 2D space, but if you add a third dimension, say tail length, suddenly a clear separating plane might emerge in this 3D space. The kernel trick does this mathematically without actually computing the high-dimensional coordinates. Popular kernels include linear kernel for already separable data, polynomial kernel for curved boundaries, RBF, Gaussian, kernel for complex, nonlinear patterns. SVM shines in high-dimensional spaces, works well with limited training data, and provides robust decision boundaries. It's particularly powerful for text classification, where you might have thousands of word features, and for image recognition tasks. The trade-off is computational complexity. SVM doesn't scale well to very large datasets, and choosing the right kernel and parameters requires careful tuning. But when you need precise, confident boundaries and can afford the computational cost, SVM delivers some of the most reliable classification performance in machine learning. Let me introduce you to the most intuitive algorithm in machine learning, k-nearest neighbors, or KNN. This algorithm learns exactly the way you learn to navigate social situations in high school. Picture this. You're the new kid walking into the cafeteria for the first time. You're holding a sketchbook, wearing a band t-shirt, and looking for somewhere to sit. To your left, there's a table of athletes in varsity jerseys, talking loudly about last night's game. To your right, there's a quieter group with art supplies spread out, sketching and talking about a gallery opening. Where do you sit? You don't need a complex decision tree or mathematical formula. You look around, find the people who seem most similar to you, and join that group. Simple, intuitive, and surprisingly effective. That's exactly how KNN works. It doesn't build a model during training. It just memorizes every single training example. Then, when a new data point comes along, it looks around the memory bank, finds K, most similar historical examples, and lets them vote on the prediction. The algorithm is beautifully simple. 1. Store all training data. This is why it's called lazy learning. 2. When a new point needs classification, calculate its distance to every single training point. 3. Find the K nearest neighbors. 4. For classification, majority vote wins. For regression, take the average. The most common distance metric is Euclidean distance, basically the straight line distance between 2 points in multidimensional space. If you have features like age, income, and credit score, Euclidean distance calculates how far apart 2 people are in this 3-dimensional space. The key decision is choosing K. If K equals 1, you're asking just the singular most similar example what the answer should be. This makes the algorithm very sensitive to noise. One weird outlier can throw off your prediction. If K is too large, you might include irrelevant neighbors that dilute the signal from truly similar examples. The general rule is to try odd numbers for K to avoid ties, and often the square root of your total number of training examples works as a reasonable starting point. Let me show you KNN in action with medical diagnosis. A new patient comes in with symptoms: fever of 101.5 degrees Fahrenheit, headache severity 7 out of 10, fatigue level 8 out of 10, and muscles ache. KNN looks through thousands of historical cases and finds the 5 most similar patients based on symptom similarity. Maybe those 5 past cases were diagnosed as flu, cold, flu, migraine. The majority vote says flu, so that becomes the prediction. The beauty of KNN is its simplicity and intuitive logic. No complex training phase, no mathematical assumptions about data distribution, no parameters to tune except k. KNN works exceptionally well when you have plenty of training data, when local patterns matter more than global trends, and when your problem naturally clusters around similar examples. It's perfect for recommendation systems. Think, people who bought items similar to your purchase history also bought these items. It excels at handwriting recognition, where similar-looking characters cluster together in feature space. But KNN has significant limitations. It's computationally expensive at prediction time because it has to calculate distances to every single training point. It struggles in high-dimensional spaces due to the curse of dimensionality, where you have hundreds of features, all distances start looking similar. It's also very sensitive to irrelevant features and requires careful feature scaling since features with larger numerical ranges can dominate the distance calculation. Despite these limitations, KNN remains one of the most interpretable algorithms in machine learning. When it makes a prediction, you can literally point to the historical examples it used and say, these are the reasons for this decision. Imagine, you've hired the world's most analytical fortune teller to detect spam emails. But instead of crystal balls and mystical intuition, she uses cold, hard probability and statistical evidence. When you bring her a suspicious email, she doesn't just give you a yes or no answer. She examines every piece of evidence systematically. She looks at the subject line. Win a free cruise! She thinks, in my experience, 80% of emails with the word win are spam, but only 5% of legitimate emails use that word. She checks the sender. No reply at prizes.xyz. She notes, emails from unknown domains ending in .xyz are spam 85% of the time. She scans the message content. Click now, limited offer, guaranteed winner. Each phrase gets evaluated. Messages containing click now are spam 90% of the time. Messages with limited offer are spam 75% of the time. Then she combines all this evidence using a mathematical framework called Bayes' theorem and announces, based on all the evidence, there's an 88% probability this email is spam. That's naive Bayes in action. It's called naive because it makes simplifying assumption that usually is wrong, but surprisingly effective. It assumes all features are independent of each other. In reality, the words in spam emails are often related. Emails that say free often also say money, and click here. But naive Bayes pretends these words appear independently and just multiplies their individual probabilities together. Here's the mathematical foundation. Bayes' theorem states that the probability of spam given the observed features equals the probability of seeing those features in spam emails times the overall probability of spam divided by the probability of seeing those features in general. For practical implementation, naive Bayes calculates what's the probability this email is spam? By looking at each word and asking, how often does this word appear in spam versus legitimate emails? The training process is beautifully simple. You count how many times each word appears in spam emails versus legitimate emails, then convert those counts to probabilities. No complex optimization, no iterative training, just counting and dividing. When a new email arrives, you look up the probability of each word being associated with spam, multiply them together, that's the naive independence assumption, and compare the result to the probability of the email being legitimate. Naive Bayes excels in several scenarios. It's incredibly fast. Both training and prediction happen in linear time. It works well with small datasets where complex algorithms would overfit. It handles high-dimensional data gracefully, making it perfect for text classification where you might have thousands of unique words as features. It's also surprisingly robust. Even though the independent assumption is violated, the relative ranking of probabilities often remains correct, which is all you need for classification. Gmail's spam filter, sentiment analysis on social media, medical diagnosis based on symptoms, and real-time news categorization all rely heavily on naive Bayes algorithms. The algorithm comes in different flavors for different data types. Multinomial naive Bayes for word counts, Gaussian naive Bayes for continuous features, and Bernoulli's naive Bayes for binary features. using naive Bayes when you need fast, simple classification, when you're working with text data, when features are relatively independent, or when you need a baseline that's easy to implement and understand. Avoid it when features are strongly correlated, when you need to capture complex feature interactions, or when you have abundant data and computational resources for more sophisticated algorithms. Imagine you've hired a cleaning crew for your messy apartment. But instead of everyone working at once, they work like a relay team of perfectionists. The first cleaner comes in and tackles all the obvious dirt, sweeping floors, wiping counters, making beds. They do a decent job, but they miss some spots. Corners are still dusty, there are stains they couldn't remove, and some areas just didn't get the attention they needed. So the second cleaner arrives, but here's the key. They don't start from scratch. They focus specifically on everything the first cleaner missed. Those dusty corners? That's their specialty now. Those stubborn stains? That's exactly what they're trained to handle. Then a third cleaner comes in, again focusing only on what the first two missed. And a fourth, and a fifth, each one becoming an expert at fixing the specific mistakes left by everyone before them. That's the core philosophy behind gradient boosting. Instead of trying to build one perfect model, you build a sequence of simple models where each one learns to correct the errors made by all the previous models combined. The mathematical elegance is in the name, gradient, because we're following the gradient of the loss function, the mathematical direction that most reduces our errors. And boosting because each new model boosts the performance of the ensemble. Here's how it works step by step. We start with a simple prediction, often just the average of all target values. The first model will have lots of errors, called residuals. Then we train a second model, but instead of trying to predict the original targets, this model tries to predict those residual errors. Where did the first model underestimate? Where did it overestimate? The second model learns to make corrections. We add this second model's predictions to the first model's predictions. Now we have a slightly better combined model. But it still has errors, just smaller ones. So we train a third model to predict these new, smaller residual errors. Then a fourth model predict the residuals that remain after adding the third model, and we continue this process with each model in the sequence learning to fix what the previous models got wrong. The typical approach uses weak learners, usually shallow decision trees with just 2 to 6 levels. These aren't very powerful individually, but when you sequence them correctly, they create incredible accurate predictions. A learning rate parameter controls how much each new model contributes to the ensemble. A low learning rate means each model makes small corrections, requiring more models but often leading to better generalization. A high learning rate means faster training but higher risk of overfitting. Let me show you this with a practical example. Say you're predicting house prices. Your first, simple model might predict the average price of $300,000. For a luxury house worth $500,000, that's an error of $200,000. The second model learns houses with more than 3,000 square feet typically need an additional $180,000 added to the base prediction. Now your combined prediction is $480,000, with a remaining error of $20,000. Then the third model learns house in the premium neighborhood need another $15,000 on top of the size adjustment. Now you're predicting $495,000, getting very close to the actual $500,000. Each model in the sequence focuses on the patterns the previous models missed, resulting in incredibly accurate final predictions. Gradient boosting has become the go-to algorithm for many machine learning competitions and business applications because it consistently delivers high accuracy with relatively little hyperparameter tuning. Modern implementations like XGBoost, LightGBM, and CatBoost have optimized this approach with advanced features like regularization, missing value handling, and parallel processing, making gradient boosting both powerful and practical for real-world applications. Let me tell you about the most dedicated teacher you've ever seen. Every week, she gives her class a quiz. After grading, she notices certain students consistently struggle while others excel. But here's what makes her special. Instead of giving everyone equal attention the next week, she adapts. The students who failed get extra help, more practice problems, and additional focus. The students who aced the quiz, they get less attention because they've already mastered the material. After the second quiz, she adapts again. The students who are still struggling get even more focused attention, and this continues week after week, with the teacher constantly adjusting her focus based on who needs help most. By the end of the semester, even the students who started as the weakest performers have caught up, because they received the most targeted, adaptive instruction. That's exactly how AdaBoost, adaptive boosting, works. It's like the dedicated teacher, but for machine learning. AdaBoost trains a sequence of weak classifiers, typically very simple decision trees called stumps, that makes decisions based on just one feature. But here's the clever part. Instead of treating all training examples equally, AdaBoost continuously adjusts the importance of each example based on how difficult it is to classify correctly. The mathematical process is we start by giving each training example equal weight, equal importance. Then we train our first weak classifier on this equally weighted dataset. After training, we evaluate the classifier's performance. The examples that classified correctly get their weights reduced, they become less important for the next round of training. The examples it misclassified get their weights increased, they become more important. This weight adjustment is exponential. If an example was easy to classify, its weight drops significantly. If it was misclassified, its weight increases dramatically, essentially telling the next classifier, pay special attention to this difficult case. The next weak classifier trains on this re-weighted dataset. It sees the same data, but the difficult examples now shout louder in the training process. This forces the second classifier to focus on the examples the first classifier struggled with. We repeat this process many times. Each subsequent classifier becomes an expert at handling the specific types of mistakes made by all previous classifiers. But AdaBoost doesn't just combine these classifiers randomly. Each classifier gets a voting weight based on its performance. Classifiers that achieved low error rates get higher voting power in the final ensemble. Classifiers that barely performed better than random guessing get minimal influence. The final prediction combines all classifier votes weighted by their individual performance levels. It's like having a panel of experts where the most accurate experts get the loudest voices. Let me show you this with email classification. The first simple classifier might learn if the subject contains free, probably spam. This catches obvious spam but misses subtle cases like congratulations, you've qualified for our special offer. These missed examples get higher weights, so the second classifier focuses on them and might learn if the message contains congratulations plus offer, probably spam. The third classifier focuses on whatever examples the first two missed, perhaps learning if the sender domain was created recently, probably spam. Each classifier becomes an expert at recognizing the specific patterns that previous classifiers missed. AdaBoost has beautifully theoretical properties. It's proven to reduce training error exponentially under certain conditions. It automatically determines when to stop adding classifiers based on performance improvements. The algorithm works well with any weak learner. Though decision stumps are most common, it's relatively resistant to overlifting compared to other boosting models. Though, it can be sensitive to noise and outliers since it focuses heavily on difficult examples. AdaBoost was one of the first practical boosting algorithms and paved the way for more advanced methods like gradient boosting. It's still widely used today, especially in computer vision applications like face detection, where the Viola-Jones algorithm uses AdaBoost to combine simple feature detectors into highly accurate face classifiers. The key insight from AdaBoost is that by adaptively focusing on difficult examples, you can combine many simple weak classifiers into one strong, accurate classifier, proving that in machine learning, just like in education, adaptive attention to struggling cases can dramatically improve overall performance. We're about to enter completely different territory. Everything we've learned so far, linear regression, decision trees, neural networks, they all had one thing in common: training data with answers. We showed the machine examples and said, this is a cat, this is spam. This house sold for $500,000. But now, we're entering the wild west of machine learning, unsupervised learning, where there are no labels, no answers, No teacher telling the machine what's right or wrong. Just raw data and the instruction. Figure out what's interesting here. Imagine you've been dropped into a foreign city with no map, no street signs, no guidebook, and no one who speaks your language. How do you start to understand this place? You observe, you notice patterns. You see that certain buildings look similar and seem to cluster together. This might be a residential neighborhood. You notice people in business suits walking in one direction during morning hours, probably the financial district. You see families with children congregating around a specific area on weekends, likely a park or entertainment zone. Without anyone teaching you, your brain starts organizing this chaos into meaningful structure. You're discovering the hidden patterns that make the city comprehensible. That's exactly what unsupervised learning does with data. Unlike supervised learning, where we have clear objectives and can measure success against known answers, unsupervised learning is about discovery. It's the difference between being handed a test with an answer key versus being an explorer mapping unknown territory. The challenges are profound. How do you know if your algorithm found something meaningful or just random noise? How do you validate discoveries when you don't have ground truth to compare against? How do you even define what interesting means? But the rewards are enormous. Most of the world's data is unlabeled. Medical researchers have millions of patient records but don't know which patterns indicate new diseases. Marketing teams have customer behavior data but don't know how many distinct customer segments exist. Scientists have sensor data from experiments but don't know which signals indicate important phenomena. Unsupervised learning tackles several fundamental challenges. Clustering. Are there natural groups in this data? Maybe your customers fall into distinct segments you never knew existed. Maybe genetic data reveals previously unknown disease subtypes. Dimensionality reduction. Can I understand this complex data by looking at it from a simpler perspective? Maybe those 100 survey questions really measure just 3 underlying personality factors. Anomaly detection. What's unusual or suspicious in this data? Maybe certain network traffic patterns indicate security breaches. Maybe certain equipment sensors readings predict failure. Association mining. What things tend to occur together? Maybe people who buy certain products also buy other specific products. Maybe certain genes are always activated together. Here's the algorithms we're about to explore. K-means, hierarchical clustering, principal component analysis, Gaussian mixture models. These are your tools for making sense of data when you don't even know what question to ask yet. It requires a different mindset. Instead of optimizing toward a known target, you're searching for structure, patterns, and insights that might not even have names yet. Welcome to the exploratory side of machine learning, where machine becomes detectives, archaeologists, and pioneers, uncovering hidden truths in data that no human labeled or organized. Picture yourself at a massive international dance festival. Hundreds of people are dancing, but there's no organization, no clear sections, just beautiful chaos of movement. As you watch, you start noticing patterns. Over here, couples are gliding smoothly in synchronized steps. That's ballroom dancing. Over there, people are moving with sharp, rhythmic precision. Hip-hop and breakdancing. In another area, dancers sway to Latin rhythms with flowing, passionate movements. Salsa and bachata. Even without signs or announcements, your brain naturally groups the dancers by style. You've just performed clustering, organizing data into meaningful groups based on similarity. K-means clustering does exactly this, but mathematically and automatically. The algorithm starts by making a guess. Let's say you think there are 3 dance styles, so you place 3 imaginary style centers randomly in the crowd. Think of these as flags planted in random spots. Now, every dancer gets assigned to whichever flag is closest to them. Some dancers near flag 1 might actually be ballroom dancers, but some might be hip-hop dancers who just happen to be standing in that area. Here's where the magic happens. After everyone is assigned to a flag, you move each flag to the center, the average position, of all the dancers assigned to it. If mostly ballroom dancers are assigned to flag 1, the flag moves toward the heart of the ballroom dancing area. Then, you repeat the process. with flags in new positions. Some dancers will now be closer to different flags, so they get reassigned. Then you move the flags again to the new centers of their assigned groups. You keep repeating this. Assign dancers to nearest flags, move flags to group centers, reassign dancers, move flags, until the flags stop moving. When that happens, you've found stable clusters. The mathematical beauty is in the objective functions. K-means minimizes the total distance between each data point and its assigned cluster center. It's literally finding the arrangement that makes every point as close as possible to its group center. The algorithm is trying to minimize what we call within cluster sum of squares, the total of all squared distances from each point to its cluster center. When this number stops decreasing, you've found the optimal clustering for your chosen number of clusters. But here's the crucial decision. How many clusters should you look for? How many dance styles are there really? This is where the elbow method comes in. You run k-means for different numbers of clusters, 1, 2, 3, 4, and 5, and plot how much the within cluster sum of squares decreases each time you add another cluster. Initially, each new cluster dramatically improves the fit, but at some point, you hit diminishing returns. The graph looks like an arm bent at the elbow, and that elbow point suggests the natural number of clusters in your data. K-means works beautifully when your clusters are roughly spherical and similar in size. It's computationally efficient, guaranteed to converge, and produce interpretable results. But it struggles with clusters that have unusual shapes, like curve or elongated groups. It also assumes all clusters are roughly the same size and density, which isn't always true in real data. In business applications, K-means excels at customer segmentation, grouping customers by purchasing behavior, demographics, or preferences. In biology, it clusters genes with similar expression patterns. In image processing, it can segment images by grouping pixels with similar colors. The key insight is that K-means finds structure in data where none was explicitly labeled. It reveals the natural organization hiding in complex datasets, turning chaos into comprehensible groups. Imagine you're an urban planner trying to understand how cities naturally organize themselves. You could use K-means to identify distinct neighborhoods, but that would only give you one level of organization. What if you wanted to understand the full hierarchy? How streets form neighborhoods, neighborhoods form districts, districts form cities, cities form metropolitan areas, and metropolitan areas from regions. You need a method that reveals not just groups, but the relationships between groups at different levels of zoom. That's exactly what hierarchical clustering provides. It builds a family tree of your data. Let me walk you through the most common approach, agglomerative clustering, which works from the bottom up. We start with every data point at its own tiny cluster. So, if you're analyzing 100 cities, you begin with 100 clusters, each containing just one city. Now comes the systematic merging process. The algorithm looks at all possible pairs of clusters and asks, which two clusters are most similar to each other? It finds the two closest clusters and merges them into one. Now you have 99 clusters. The algorithm repeats. Find the two closest remaining clusters and merge them. Now 98. This continues until eventually everything is merged into one giant cluster containing all your data. But here's the crucial part. The algorithm records every merge and the distance at which it happened. This creates a tree-like structure called a dendrogram, literally tree drawing, that shows the complete hierarchy of relationships. The key decision is how to measure distance between clusters. This is called the linkage criterion, and it dramatically affects your results. Single linkage measures the distance between the closest points in two clusters. This tends to create elongated, chain-like clusters and is sensitive to outliers. Complete linkage measures the distance between the farthest point in two clusters. This creates more compact, spherical clusters. Average linkage takes the mean distance between all pairs of points in the two clusters, and this provides a balanced approach. Ward's method minimizes the increase in within-cluster variance when merging. This tends to create clusters of similar size and is often the most useful for practical applications. The beauty of the dendrogram is that you can cut it at any height to get different number of clusters. Cut high and you get few, broad clusters. Cut low and you get many specific clusters. Let me show you this with a concrete example. Imagine you're clustering gene expression data from cancer patients. The dendrogram might reveal that at the highest level, there are 2 main cancer types. But when you look more closely, each type splits into subtypes, and each subtype might split into further variants. This hierarchical structure provides biological insights that flat clustering methods miss. Maybe certain subtypes respond to similar treatments, or maybe the hierarchy reveals the evolutionary relationship between different cancer types. Hierarchical clustering shines when the natural structure of your data is truly hierarchical, like organizing charts, evolutionary trees, or market segments that have subcategories. It's also valuable for exploratory data analysis because you don't need to specify the number of clusters in advance. The dendrogram shows you all possible cluster counts and lets you choose the level that makes the most sense for your application. The main limitation is computational complexity. The naive algorithm requires comparing every pair of data points at each step, making it impractical for very large data sets. But for medium data sets, where understanding relationships between groups matters as much as the groups themselves, hierarchical clustering provides insights that other methods simply can't match. You're not just finding clusters, you're mapping the family tree of your data, revealing how different groups relate to each other across multiple levels of granularity. Imagine you're a photographer trying to capture the essence of complex 3-dimensional sculpture, but you can only take 2D photographs. The sculpture has intricate details, flowing curves, and multiple interconnected parts. From one angle, your photo might just show a confusing blob. From another angle, maybe you capture some interesting details but miss the overall structure. But there's one perfect angle, one specific perspective where your 2D photo captures the sculpture's most important features. Its essential character, its defining elements. That's exactly what principal component analysis does with high-dimensional data. It finds perfect camera angles and optimal perspectives that capture the most important information while reducing complexity. Let me show you why this matters. Imagine you're analyzing customer data with 50 different features: age, income, purchase history, website clicks, social media activity, geographic location, and 44 other variables. Trying to understand patterns in 50-dimensional space is impossible for human brains to visualize or interpret. But what if those 50 dimensions really represent just 2 or 3 underlying factors? Maybe there's a spending power dimension that combines income, purchase history, and premium product preferences. Maybe there's a digital engagement dimension that combines website activity, social media usage, and other online purchase frequency. PCA automatically discovers these underlying dimensions called principal components that explains the most variation in your data. Here's how it works mathematically. PCA looks at all your data and asks, what direction shows the maximum spread, the maximum variation? That becomes the first principal component. Then it asks, what direction, perpendicular to the first, shows the next most variation? That's the second principal component. And it continues this process, finding new directions that are perpendicular to all previous ones and capture the most remaining variation. The mathematical foundation involves eigenvalue decomposition of the covariance matrix. But let me translate that into intuitive terms. Imagine your data as a cloud of points in high-dimensional space. PCA finds the axis that best describes the shape of that cloud. If your data cloud is elongated like a cigar, the first principal component runs along the length of the cigar, the direction of maximum variation. The second component runs along the width, the third along the height. Here's the powerful part. Often, the first few principal components capture most of the interesting variation in your data. Maybe 3 components explain 85% of the variation that was originally spread across 50 dimensions. This enables incredible compression and visualization. You can project your 50-dimensional customer data onto just 2 dimensions and create scatterplots that reveal customer segments, outliers, and patterns that were invisible in the original high-dimensional space. PCA is also fantastic for noise reduction. If your original data has 50 dimensions, but the first 10 principal components capture 95% of the variation, then dimensions 11 through 50 are mostly noise. By keeping only the first 10 components, you clean your data while preserving almost all the meaningful information. Real-world applications are everywhere. In image processing, PCA can compress photos by representing them in terms of the most important image patterns. In finance, it can identify the main factors driving stock market movements. In genetics, it can reveal population structure from genetic variation data. The limitation is that PCA assumes linear relationships. If your data has complex, nonlinear patterns, PCA might miss important structures. Also, the principal components might not have intuitive interpretations. The first component might be a complex combination of many original features that's hard to explain in business terms. But when you need to understand high-dimensional data, reduce noise, and compress information, or visualize complex patterns, PCA provides an elegant mathematical framework for finding the most informative perspectives in your data. It's like having a master photographer who always knows the perfect angle to capture the essence of any scene, no matter how complex. Let's go back to the dance festival, but this time with a more nuanced perspective. K-means clustering looked at the dancers and said, you belong to the ballroom group, you belong to the hip-hop group, you belong to the salsa group. Clean, discrete assignments. But reality is messier than that. What about the dancer who knows both ballroom and hip-hop? What about someone standing right at the boundary between 2 groups? What about dancers who incorporate multiple styles into their movement? Gaussian mixture models, or GMM, handles the complexity beautifully. Instead of making hard assignments, GMM says, you're 70% likely to be in the ballroom group, 25% likely to be in the hip-hop group, and 5% likely to be in the salsa group. This probabilistic approach captures the reality that boundaries between groups are often fuzzy, and individuals might partially belong to multiple groups. Here's the core insight. GMM assumes your data comes from a mixture of several Gaussian distributions. Imagine multiple bell curves overlapping in multidimensional space. Each Gaussian represents a different cluster, but unlike K-means, these clusters can have different shapes, sizes, and orientations. Think of each Gaussian as a probability cloud. Some clouds might be tall and narrow, representing tightly clustered groups. Others might be wide and flat, representing more spread out groups. Some might be tilted at angles, representing groups with correlated features. The mathematical elegance is in the expectation maximization algorithm that learns these Gaussian parameters. It starts with initial guesses for each Gaussian mean, covariance, and mixing weight, then iteratively improves these estimates. In the expectation step, for each data point, the algorithm calculates the probability that it belongs to each Gaussian cluster. This is like asking, given what I currently believe about each group, how likely is this dancer to belong to each group? In the maximization step, the algorithm uses these probability assignments to update its belief about each Gaussian. It recalculates the mean, covariance, and mixing weight for each cluster based on the probabilistic assignments from the E step. This process repeats until convergence, when the parameters stop changing significantly between iterations. Let me show you why this matters with a business example. Imagine you're segmenting customers for a streaming service. K-means might put customers into discrete categories: comedy lovers, drama fans, action enthusiasts. But GMM recognizes that real customers are more complex. Maybe someone is 60% a comedy lover, 30% a drama fan, and 10% action enthusiast. This probabilistic membership allows for much more nuanced marketing strategies. You could send comedy recommendations with high confidence, occasionally suggest dramas, and rarely recommend action movies. This personalized approach based on probabilistic cluster membership often performs much better than one-size-fits-all segment marketing. GMM also provides uncertainty estimates. If a customer has low probabilities across all clusters, maybe 35, 33, and 32%, You know this is a boundary case that doesn't fit well into any group. These customers might need special attention or represent opportunities to discover new segments. The algorithm naturally handles clusters of different sizes and shapes. Unlike k-means, which assume all clusters are roughly spherical and equal sized, GMM can discover elongated clusters, dense clusters mixed with sparse clusters, and clusters with different orientations entirely. Model selection. Choosing the optimal number of components. Uses information criteria like AIC or BIC that balance model fit against complexity. Too few components miss important structure. Too many components overfit to noise. GMM excels in applications where soft membership makes sense, customer segmentation with overlapping preferences, medical diagnosis where patients might have multiple conditions, and financial modeling where investments might belong to multiple risk categories. The trade-off is computational complexity and the assumption that your data really does come from Gaussian distributions. If your clusters have very non-Gaussian shapes, GMM might struggle. But when you need probabilistic cluster assignments, when you want to capture uncertainty in your groupings, or when your clusters have complex shapes and sizes, GMM provides a principled, flexible framework that captures the messy reality of real-world data far better than hard clustering models. Everything we've learned so far has been building toward this moment. We're about to enter the realm that has transformed artificial intelligence from a research curiosity into a technology that's reshaping every industry on the planet. Deep learning represents a fundamental shift in how we approach machine learning. Instead of carefully engineering features and choosing algorithms, deep learning builds artificial brains that learn to perceive, understand, and create in ways that often surpass human capabilities. Think about how your brain processes the world. When you see a cat, you don't consciously analyze pixel intensities, edge gradients, and texture patterns. Your visual system processes information hierarchically. Your retina detects light and dark patterns, your early visual cortex recognizes edge and simple shapes, and deeper regions combine these into textures and parts, ears, whiskers, fur patterns. Even deeper regions recognize cat as a complete concept, connected to memories, emotions, and knowledge about cats. This hierarchical processing, from simple features to complex concepts, is exactly what deep neural networks do artificially. The revolution started when we realized three things converged at the same time. First, we finally had enough data. The internet, social media, smartphones, and digital sensors created datasets with millions or billions of examples, far more than traditional machine learning ever had access to. Second, we had enough computational power. Graphics processing units, originally designed for video games, turned out to be perfect for matrix operations that neural networks require. What once took months of computation could now be done in hours. Third, we had algorithmic breakthroughs. Better activation functions, improved optimization techniques, new architectures, and regularization methods solved problems that had plagued neural networks for decades. The result has been extraordinary. Deep learning now powers the voice assistant in your phone, automatically translates between hundreds of languages, creates realistic images from text descriptions, writes computer code, plays strategy games at superhuman levels, predicts protein structures, and drives cars autonomously. But here's what makes it truly revolutionary. Deep learning systems often discover patterns and representations that humans never thought to look for. They don't just mimic human intelligence, they often exceed it by finding entirely different ways to solve problems. A deep learning system trained to diagnose medical images might discover the tiny variations in pixel intensity completely invisible to human doctors. Consistently predict disease progression. A language model might learn grammatical patterns that linguists never formally described. This brings us to one of the most important concepts in modern AI: representation learning. Instead of us telling the machine what features to look for, deep learning systems automatically discover the best representations for their tasks. The power comes from depth, multiple layers of processing where each layer builds more abstract representations from the layers below. Early layers might detect edges and textures, middle layers might recognize parts and patterns, and deep layers might understand concepts and relationships. Over the next few minutes, we're going to explore the key architectures that make this possible. Feed-forward networks that approximate any function. Convolutional networks that see and understand images. Recurrent networks that process sequences and times. And transformers that have revolutionized natural language understanding. Each architecture solves specific types of problems, but they all share the core principle. Build artificial neural networks deep enough and wide enough, give them enough data and computational resources, and they can learn to solve problems that seemed impossible just a few years ago. Welcome to the era where machines don't just follow our instructions. They learn to see, understand, and create in ways that complement and sometimes surpass human intelligence. Let's take a step inside the most successful coffee shop in the city, where the barista has an almost supernatural ability to predict what customers want. When a customer walks in, the barista doesn't just see a random person. Her brain processes information in layers, like a perfectly choreographed sequence. First layer, visual recognition, age, gender, clothing style, expression, basic observable features. Second layer, pattern matching. This person looks like the type of person who orders a complex drink. The laptop bag suggests they'll be here for a while. The fitness tracker indicates health consciousness. And the third layer, the context integration. It's 3 p.m. on a Tuesday. Most health-conscious laptop users at this time want something caffeinated but not too heavy. Probably an oat milk latte. And your output layer, decision. I'll start preparing an oat milk latte and ask if they want their usual when they approach. This layered processing from raw inputs to complex decisions is exactly how feed-forward neural networks work. Information flows in one direction through layers of artificial neurons, with each layer building more sophisticated understanding from the layers before. Let me show you the mathematical foundation. Each artificial neuron performs a simple but powerful operation. It takes weighted inputs, adds them up, adds a bias term, and passes the result through an activation function. The formula is output equals activation function of the sum of weighted inputs plus bias. Mathematically, that's activation. The weights determine how much attention each neuron pays to different inputs. High positivity weights mean this input strongly supports activation. Large negative weights mean this input strongly opposes activation. The bias lets the neuron have a baseline tendency to activate or not. The activation function is crucial. It introduces nonlinearity that enables the network to learn complex patterns. The most popular choice is ReLU, Rectified Linear Unit, which simply outputs the input if it's positive, zero otherwise. It's like saying only pass along positive signals. Here's how information flows through the network. The input layer receives raw data, maybe pixel values from an image or numerical features like age and income. Each neuron in the first hidden layer combines these inputs with learned weights, producing a new representation. These first layer outputs become inputs to the second hidden layer, which creates even more abstract representations. This continues through multiple layers until the output layer reproduces final predictions. The magic happens during training through backpropagation. The network makes predictions, compares them to the correct answers, calculates the error, then works backward through all the layers, adjusting weights to reduce future errors. It's like our coffee shop barista getting feedback. If she predicts an oat milk latte, but the customer orders black coffee, she adjusts her internal model. Laptop bag plus fitness tracker doesn't always mean health-conscious drink choice. Maybe I should pay more attention to the time of day and facial expression. Let me show you this with a practical example. Handwritten digit recognition. The input layer receives a 28 by 28 pixel image, 784 numbers representing light and dark pixels. The first hidden layer might learn to detect simple features, horizontal lines, vertical lines, curves, corners. Each neuron becomes specialized for recognizing specific low-level patterns. The second hidden layer combines these simple features into more complex shapes, loops, intersections, specific digit parts. Maybe one neuron fires strongly when it sees loop at the top with vertical line below, indicating a 9 or a P. The output layer has 10 neurons, one for each possible digit. The neuron with the highest activation determines the final prediction. The beautiful part is that we never told the network what features to look for. Through training on thousands of examples, it automatically discovered that edges, curves, and specific combinations matter for digit recognition. Feed-forward networks are universal function approximators. Given enough neurons and layers, they can theoretically learn any continuous function mapping, inputs to outputs. This makes them incredibly versatile. They excel at problems with structured input data where spatial relationships don't matter, like predicting house prices from numerical features, classifying medical diagnosis from test results, or recommending products based on user profiles. The key insight is that each layer learns increasingly abstract representations. Raw inputs become features, features become patterns, patterns become concepts, and concepts become decisions. This hierarchical feature learning, where the networks discover its own representations rather than using handcrafted features, is what makes deep learning so powerful and why feed-forward networks form the foundation for more specialized architectures we'll explore next. Imagine you're an art critic examining a complex painting for the first time. You don't try to understand the entire piece all at once. Instead, your eye naturally follows a systematic process. First, you notice basic visual elements, lines, edges, color contrast, textures. Then your brain starts combining these elements into shapes and patterns. Gradually, you recognize object, faces, scenes. Finally, you understand the overall composition, meaning an artistic message. This hierarchical visual processing, from local details to global understanding, is exactly what convolutional neural networks revolutionized in computer vision. Traditional approaches to image recognition tried to analyze every pixel simultaneously, like trying to understand a book by looking at all the letters at once. CNNs instead process images the way human vision works, systematically, hierarchically, and with attention to spatial relationships. The core innovation is the convolution operation. Imagine sliding a small magnifying glass across an image, examining just a tiny patch at a time. At each position, you're asking, does this small area contain a specific pattern I'm looking for? That magnifying glass is called a filter or kernel, typically a 3x3 or 5x5 grid of numbers. As it slides across the image, it performs element-wise multiplication with the underlying pixels, then sums the results. This produces a single number indicating how well that image patch matches the filter's pattern. For example, a vertical edge detector might look like -1, 0, +1, repeated in rows. When this slides over an image, it responds strongly to vertical boundaries between light and dark regions, exactly where vertical edges appear. But here's the beautiful part. CNN doesn't use handcrafted filters. During training, it learns what filter patterns are most useful for the specific task. The network automatically discovers which local patterns matter most for distinguishing cats from dogs, or identifying traffic signs, or detecting medical anomalies. A typical CNN architecture follows a systematic pattern. Convolutional layers apply learned filters to detect local patterns. Each filter produces a feature map highlighting where that pattern appears in the image. Activation layers, usually ReLU, introduce non-linearity, keeping only positive responses and discarding negative ones. This creates sparse, selective responses to important patterns. Pooling layers downsample the feature maps, typically by taking the maximum value in small regions. This creates translation invariance. The network recognizes patterns regardless of their exact position and reduces computational requirements. Let me walk you through how a CNN processes an image of a cat. The first convolutional layer applies dozens of filters, learning basic visual elements, horizontal edges, vertical edges, curves, color gradients, and texture patterns. The second layer combines these basic elements into more complex shapes, corners where edges meet, specific texture combinations, simple geometric forms that commonly appear in cat photos. The third layer recognizes cat-specific parts, triangular ears, whiskers, fur patterns, eye shapes, nose structures. Each neuron becomes specialized for detecting specific anatomical features. Deeper layers understand complete object and scenes. Cat face, cat in sunlight, tabby cat pattern. Integrating information from earlier layers into a holistic recognition. The final layers make the classification decision based on all this hierarchical analysis. Instead of looking at raw pixels, they're making decisions based on high-level concepts like pointy ears plus whiskers plus fur equals cat. This spatial hierarchy is what makes CNNs so powerful for visual tasks. They automatically learn the right features at the right level of abstraction, from pixel-level details to object-level concepts. The parameter sharing is elegant and efficient. The same edge detector filter that works in the top left corner of an image also works in the bottom right corner. This dramatically reduces the number of parameters compared to fully connected networks, while making the system translation invariant. CNNs have revolutionized computer vision applications. Medical image analysis detecting tumors invisible to human doctors. Autonomous vehicles recognizing pedestrians and traffic signs. Smartphones organizing your photos by recognizing faces and objects. Security systems identifying suspicious activities. But the principles extend beyond traditional images. 1D CNNs analyze time series data and audio signals. 3D CNNs process video and medical volumetric data. The convolution operation works wherever local patterns and spatial relationships matter. The key insight is that by processing information locally and hierarchically, CNNs capture the natural structure of visual information, enabling machines to see and understand images with accuracy that often exceeds human performance. Think about a master pianist performing a complex sonata. She doesn't play each note in isolation, forgetting what came before. Every note is influenced by the musical context, the melody line that's been building, the harmonic progression that's developing, the emotional arc of the entire piece. When she plays a C sharp, it might be melancholy in the context of a minor key passage, but triumphant as part of a major key resolution. The same note has completely different meaning depending on the sequence of notes that preceded it. This is the fundamental challenge that the recurrent neural networks solve. How to process sequences where context and order matter crucially, where understanding depends not just on current input, but on everything that came before. Traditional feed-forward networks process each input independently. Show them the word bank, and they have no idea whether you're talking about a financial institution or the side of a river. But RNNs maintain memory across time steps, building understanding that accumulates with each new piece of information. The mathematical elegance is in the recurrent connection. At each time step, an RNN takes two inputs: the current data and its own previous hidden state. It's memory from the last time step. It combines these to produce both an output and an updated memory state that carries forward to the next step. The formula is h of t equals activation of w times x of t, plus u times h of t minus 1 plus bias, where h of t is the current hidden state, x of t is the current input, and h t minus 1 is the memory from the previous step. W and U are learned weight matrices that determine how to combine current input with past memory. This creates a chain of memory flowing through time, h of 1 to h of 2 to h of 3 to h of t. Each hidden state contains compressed information about everything the network has seen up to that point. Let me show you this with language translation. Consider translating "the cat that was sleeping in the garden is now awake" into French. A RNN processes this word by word. Remember we're starting a noun phrase. Cat, store that the subject is cat. Gender matters for French. That begins relative clause. Still need to remember cat is the main subject. Was sleeping. Past continuous tense, but keep tracking the main subject. In the garden. Location context, but cat is still the key subject. Is now awake. Present tense predicate. finally can complete Le chat qui dormait dans le jardin est maintenant éveillé. The RNN maintains context across the entire sentence, remembering that cat is masculine in French, so all related adjectives and articles must agree, even when the sentence is long and complex. This memory capability makes RNNs powerful for many sequential tasks. In speak recognition, they maintain context about the speaker's accent, speaker pace, and topic to better interpret ambiguous sounds. In financial modeling, they remember market trends and economic indicators across time to predict future prices. For text generation, RNNs can write in consistent styles by remembering the vocabulary, tone, and structural patterns they've been learning. They can maintain character personalities across long narratives or technical accuracy across complex explanations. But RNNs face a fundamental challenge called the vanishing gradient problem. When training very long sequences, the mathematical signals that update earlier time steps become exponentially weak. The network can remember recent context clearly, but forgets important information from many steps ago. It's like trying to remember a conversation from last week. You might recall recent points clearly, but crucial details from the beginning become fuzzy. For RNNs, processing long documents or extended time series, this memory degradation severely limits their effectiveness. This limitation led to more sophisticated architectures, like LSTMs and GRUs, which use gating mechanisms to selectively maintain long-term memory. But the core insight remains. For any problem involving sequences, context, and temporal dependencies, you need networks that can accumulate and maintain relevant information across time. Whether it's understanding language, processing sensor data, analyzing financial markets, or generating creative content, RNNs and their successors provide the memory mechanisms that make sequential intelligence possible. The key breakthrough was realizing that intelligence often isn't about processing individual data points. It's about understanding patterns, relationships, and meanings that emerge across sequences of related information. Let me tell you about the most organized personal assistant you've ever imagined. This assistant manages your complex life with 3 simple but powerful rules. First, she decides what information to forget. The meeting from last month that got canceled? I'm forgetting that completely to make room for more important things. Second, she decides what new information to remember. The new project deadline is crucial. I'm storing this in long-term memory with high priority. Third, she decides what stored information to bring forward when you need to make decisions. You're asking about next week's schedule? Let me pull up all relevant appointments and deadlines that affect those decisions. This selective intelligent memory management is exactly how long short-term memory networks, LSTMs, revolutionized sequence processing by solving the memory problems that plagued simpler RNNs. The breakthrough insight was that memory needs to be managed, not just accumulated. Instead of letting information decay gradually over time, LSTMs use sophisticated gating mechanisms to actively control what information flows through the network. The architecture has 2 types of memory, cell state and hidden state. Think of cell state as long-term storage, the assistant's filing cabinet that can maintain information across hundreds or thousands of time steps. Hidden state is working memory, the information currently active and available for processing. The genius is in 3 gates that control information flow. The forget gate looks at current input and previous hidden state and decides, what information from long-term memory should I discard? It outputs values between 0 and 1, where 0 means completely forget and 1 means completely retain. The input gate works in 2 parts. First, it decides what new information deserves to be stored in long-term memory. Second, it creates candidate values, new information that could potentially be added. The input gate then filters these candidates, storing only what's deemed important. The output gate controls what parts of long-term memory should influence current processing. It's like the assistant deciding, of everything I know, what's relevant for this current task. Let me show you this with machine translation of a complex sentence. The company that was founded in Silicon Valley in 1995 and later moved to Seattle has now announced its expansion into European markets. A simple RNN would struggle to maintain the connection between company at the beginning and has announced near the end. The subject-verb relationship gets lost in the middle complexity. But an LSTM handles this elegantly. Early in the sentence, the input gate stores company in cell state with high retention value. As it processes the relative clause, that was founded in Silicon Valley in 1995, the forget gate maintains the main subject while the input gates adds temporal and location context. And later moved to Seattle, adds more detail without forgetting the main subject. When reaching has now announced, the output gate retrieves the stored subject information, enabling proper grammatical agreement and translation. This selective memory management enables LSTMs to handle much longer sequences than simple RNNs. They can translate entire paragraphs while maintaining coherent subject-verb agreement, generate stories with consistent character development across many sentences, or analyze time series data with long-term dependencies. The mathematical formulation involves 3 sigmoid gates: forget, input, and output, and 1 ton layer, candidate values. Each gate outputs values between 0 and 1, controlling how much information passes through. The cell state flows through the network with minimal modifications, providing a stable highway for long-term information. Training LSTMs require backpropagation through time, but the gating mechanisms provide more stable gradients than simple RNNs, enabling effective learning of long-range dependencies. LSTMs excel in applications where long-term context matters. Machine translation maintaining grammatical consistency across long sentences. Speech recognition, understanding speakers across extended utterances. Financial modeling, considering long-term market trends. And medical diagnosis, integrating symptoms across extended patient histories. The key insight is that effective sequence processing requires not just memory, but intelligent memory management, knowing what to remember, what to forget, and what to recall for current decisions. While transformer architectures have largely superseded LSTMs for many natural language tasks, the principles of gated memory remain fundamental to sequence modeling, and LSTMs continue to excel in many time series and signal processing applications, where their inductive biases match the problem structure. Imagine you're at the most fascinating cocktail party ever. Dozens of conversations happening simultaneously, each with their own context, nuances, and importance levels. Unlike most people who can only focus on one conversation at a time, you have a superpower. You can pay attention to every conversation simultaneously, but with different levels of focus based on relevance to your current needs. When someone mentions your name across the room, you instantly tune into that conversation while still monitoring others. When someone discusses a topic you're passionate about, you focus more attention there. When someone starts telling a story that connects to multiple others' conversations, you track all those connections simultaneously. This supernatural ability to selectively attend to relevant information across multiple parallel streams is exactly what the transformer architecture brought to machine learning. And it has revolutionized artificial intelligence. The core innovation is the attention mechanism, which asks a fundamental question. For every word in this sentence, which other words are most important for understanding its meaning? Consider the sentence. The animal didn't cross the street because it was too tired. When processing the word it, a human immediately knows it refers to animal, not street. But for a machine, this requires sophisticated reasoning and grammatical relationships, semantic meaning, and contextual relevance. The attention mechanism solved this by creating 3 representations for each word. Query, what am I looking for? Key, what information do I contain? And value, what information can I provide? For the word it, the query representation asks, what noun could this pronoun refer to? The key representations from animal and street indicate what each word contains. The attention mechanism calculates that animal has a much higher relevance to it than street does. Mathematically, attention computes the similarity between the query and all keys, convert these similarities to probabilities using softmax, then combines the values weighted by these probabilities. The result is a context-aware representation that incorporates relevant information from across the entire sequence. But transformers go further with multi-head attention, running multiple attention mechanisms in parallel, each focusing on different types of relationships. One head might specialize in grammatical dependencies, another in semantic relationships, another in positional patterns. This parallel processing is revolutionary. Unlike RNNs that process sequences step by step, transformers process all positions simultaneously. Every word can directly attend to every other word in a single computational step. This enables massive parallelization and captures long-range dependencies without the memory decay problems of RNNs. The complete transformer architecture stacks multiple layers, each containing multi-head attention followed by position-wise feedback networks. Residual connections and layers normalization ensure stable training of very deep networks. For sequential tasks like translation, transformers use an encoder-decoder structure. The encoder processes the input sequence, building rich representations that capture all internal relationships. The decoder generates the output sequence, using attention to focus on relevant parts of the encoded input. Positional encoding solves the problem that attention is inherently position agnostic. Since attention only considers content similarity, the model needs additional signals to understand that cat-dog and dog-cat are different sequences. The impact has been extraordinary. Transformers power GPT models that generate human-like text, BERT models that understand reading comprehension, translation systems that handle dozens of languages, and increasingly, models that process images, audio, and multimodal data. The key insight is that many AI tasks involve understanding complex relationships across elements in a sequence or set. Traditional approaches either processed elements independently, losing relationship information, or sequentially, limiting parallelization and long-range modeling. Transformers enable direct modeling of all pairwise relationships while maintaining full parallelization. Every element can attend to every other element, weighted by learned relevance, creating rich representations that capture complex dependencies. This attention-based approach has proven so powerful that it's expanded beyond natural language processing into computer vision, speech recognition, protein folding prediction, and even reinforcement learning. The transformer didn't just improve existing tasks. It enabled capabilities that seemed impossible just a few years ago, like generating coherent multi-paragraph text, engaging in contextual conversations, and solving complex reasoning problems through language and understanding. Okay, forget everything you know about traditional machine learning just for a moment. No labeled datasets, no correct answers, no teachers showing examples. Instead, imagine learning the way you learn to ride a bicycle, play chess, or navigate a new city. You try something. You observe the consequences. You adjust your approach based on whether those consequences were good or bad. You try again, gradually through trial and error, reward and punishment. You develop skills and strategies that lead to success. This is reinforcement learning, machine learning's closest approximation to how humans and animals actually learn complex behaviors in the real world. Think about training a dog. You don't show your dog thousands of labeled examples of good sitting versus bad sitting. Instead, when your dog sits on command, you give a treat. When your dog ignores the command, no treat. Over time, your dog learns that sitting leads to rewards, so sitting behavior becomes more frequent. Reinforcement learning works on exactly the same principle, but with mathematical precision. The framework involves an agent, the learner, interacting with an environment. At each moment, the agent observes the current state of the environment, chooses an action based on its current policy, executes that action, and receives two things: a reward signal and the new state that results from the action. The agent's goal is to learn a policy, a strategy for choosing actions, that maximizes the total reward it receives over time. Not just immediate reward, but the cumulative reward across long sequences of interactions. This creates fascinating challenges that don't exist in supervised learning. The exploration versus exploitation dilemma. Should the agent choose actions it knows work well, or try new actions that might lead to even better outcomes? Credit assignment. If the agent receives a reward after a long sequence of actions, which actions actually contributed to that reward? Delayed consequences. The best immediate action might lead to poor long-term outcomes, while actions that seem suboptimal in the short term might set up better future opportunities. Let me show you this with a game. Consider an AI learning chess. Initially, it knows the legal moves but has no strategy. It makes random moves and usually loses quickly. But occasionally, through random exploration, it wins a game. The reinforcement learning algorithm examines the sequence of moves that led to victory and increases the probability of making similar moves in similar positions. Over thousands of games, the AI gradually develops an understanding. Certain opening moves lead to better positions. Controlling the game's center is valuable. Protecting the king is crucial. A material advantage usually leads to victory. Crucially, no human programmed these chess strategies. The AI discovered them through experience, trial and error, and mathematical optimization of reward signals. Mathematical foundation involves value functions, estimates of how good it is to be in a particular state or to take particular actions. The agent constantly updates these estimates based on experience, using algorithms like Q-learning or policy gradients. Modern deep reinforcement learning combines neural networks with RL algorithms, enabling agents to learn in environments with enormous state spaces. AlphaGo learned to play Go at superhuman levels. OpenAI 5 mastered the complex real-time strategy game Dota 2. Autonomous vehicles learn driving policies through simulation and real-world experience. The applications extend far beyond games. Recommendation systems learn to suggest content that maximizes user engagement. Trading algorithms learn to make investment decisions that maximize returns while managing risk. Data center cooling systems learn to minimize energy consumption while maintaining optimal temperatures. Robotic systems learn manipulation skills, walking gaits, and navigation strategies through physical interaction with the world. Drug discovery systems learn to design molecules with desired properties through virtual experimentation. The power of reinforcement learning lies in its generality. Any problem that can be framed as sequential decision-making under uncertainty, where an agent must learn through interaction to achieve goals, can potentially be solved with RL. But RL also presents unique challenges. Sample efficiency. Learning through trial and error can require millions of interactions. Safety. Exploration during learning might lead to dangerous or costly mistakes. Generalization. Policies learned in one environment might not transfer to slightly different conditions. Despite these challenges, reinforcement learning represents our best approach to creating truly autonomous systems that can learn, adapt, and improve their performance through experience in complex, dynamic environments. It's the closest we've come to artificial general intelligence. Systems that don't just recognize patterns in static data, but actively learn to navigate and succeed in complex, interactive world around them. Imagine you're an explorer who's been dropped into a completely unknown maze. There are treasures scattered throughout, but also dangerous traps. You have no map, no guide, no prior knowledge, just the ability to move, observe, and learn from experience. At first, you move randomly, trying different paths. Sometimes you find treasures, sometimes you trigger traps. Sometimes you just wander through empty corridors. But you're smart. You keep a detailed notebook of your experiences. From room A, going right led to a treasure worth 10 points. From room B, going left led to a trap that cost me 5 points. From room C, going forward eventually led to the exit with a 50-point bonus. Over time, your notebook becomes a comprehensive guide from any position in the maze. You know which action is likely to lead to the best long-term outcomes. That notebook is your Q table, and the learning process is Q learning. Q learning is one of the most elegant algorithms in machine learning because it learns optimal behavior without needing a model of the environment. It doesn't need to understand how the maze is constructed or predict where each action will lead. It simply learns from experience which actions lead to the best outcomes. The Q stands for quality, specifically the quality or value of taking a particular action in a particular state. Q, state action, represents the expected total reward from taking that action in that state, then acting optimally afterward. The mathematical beauty is in the update rule. Every time the agent takes an action and observes the result, it updates its Q value estimate using this formula. Q state action gets updated by adding a learning rate times the temporal difference error. The temporal difference error is the difference between what actually happened, the immediate reward, plus the best possible future value, and what that agent previously expected from the state action pair. Let me break this down with our maze example. Suppose your Q table currently estimates that from room A, going right has a value of 5 points. But when you actually go right from room A, you immediately get 10-point reward and end up in room D, where your best action has an estimated value of 8 points. The temporal difference error is 10 plus 8 minus 5, which equals 13. This large positive error tells you that going right from room A is much better than you previously thought, so you increase that Q value. This process repeats thousands of times. Gradually, the Q values converge to the true optimal values, the actual expected returns from each state action pair when acting optimally. The key insight is that Q learning is off policy. It learns about the optimal policy regardless of which policy it's currently following. Even when the agent explores randomly or makes suboptimal choices, it learns what the best choices would be. This enables a powerful exploration strategy called epsilon greedy. Most of the time, the agent chooses the action with the highest Q value, exploitation. But with some small probability, epsilon, it chooses a random action, exploration, and this ensures the agent continues discovering new possibilities while primarily following its current best strategy. Q learning has been applied successfully to many domains. In robotics, robots learn navigation strategies by exploring environments and receiving rewards for reaching goals while avoiding obstacles. In finance, trading algorithms learn to make buy-sell decisions by receiving rewards based on profit and loss. Game-playing AI systems use Q learning to master strategy games. The algorithm learns that certain positions are valuable, certain moves lead to winning advantages, and certain sequences of actions maximize long-term success. The algorithm's main limitation is scalability. Traditional Q learning requires storing Q values for every possible state action pair. In complex environments with millions or even billions of possible states, this becomes computationally intractable. This limitation led to deep Q networks, DQNs, which use neural networks to approximate Q values instead of storing them in tables. This enables Q learning in high-dimensional environments like video games with complex visual inputs. But the core principle remains. By systematically exploring an environment and learning from the rewards and consequences of actions, an agent can discover optimal policies for achieving goals, even in environments it has never seen before. Q learning proves that optimal decision-making can emerge from experience alone, without prior knowledge or explicit instruction. A powerful demonstration of learning through interaction with the world. We started this journey with a simple question. How do machines learn? And now, after exploring algorithms from linear regression to transformers, from k-means to Q learning, you have the answer. Machines learn the same way you learn to recognize faces, understand language, and navigate the world, through patterns, experience, and iterative improvement. The difference is that we've mathematized these learning processes, giving machines precise algorithms for discovery, prediction, and decision-making. Think about what you've accomplished. You now understand supervised learning, how machines learn from examples with known answers. You've seen how linear regression finds straight-line relationships, how decision trees ask systematic questions, how neural networks build hierarchical understanding, and how ensemble methods combine multiple perspectives for robust predictions. You've explored unsupervised learning, how machines discover hidden structure in data without guidance. You know how k-means find natural groupings, how PCA reveals essential perspectives in high-dimensional data, and how hierarchical clustering builds family trees of relationships. You've delved into deep learning, how artificial neural networks process information hierarchically from simple features to complex concepts. You understand how CNNs see and understand images, how RNNs and LSTMs process sequences with memory, and how transformers revolutionized AI through attention mechanisms. You've discovered reinforcement learning, how machines learn optimal behaviors through trial, error, and reward feedback, developing strategies for complex sequential decision-making. But more importantly, you've developed machine learning intuition. You know that algorithm choice depends on your problem type, data characteristics, and performance requirements. You understand fundamental trade-offs, bias versus variance, interpretability versus accuracy, simplicity versus sophistication. You recognize that machine learning isn't magic. It's mathematical pattern recognition applied systematically to data. The intelligence emerges from algorithms designed to minimize errors, maximize rewards, or discover structure through optimization and statistical inference. This knowledge makes you a more informed citizen in an AI-driven world. When you see news about breakthrough AI systems, you understand the underlying principles. When businesses claim AI-powered solutions, you can evaluate whether the application makes technical sense. When you encounter algorithmic decisions in your life, you understand how they might work and what their limitations might be. But this is just the beginning of your machine learning journey. The field evolves rapidly. New architectures, improved algorithms, novel applications emerge constantly. The foundation you've built enables you to understand and adapt to these advances. Your next steps depends on your goals. If you're interested in practical application, start implementing these algorithms on real datasets. Kaggle competitions provide excellent practice with genuine problems and data. GitHub repositories offer code examples and projects to explore. If you're drawn to research and innovation, dive deeper into the mathematical foundations. Study optimization theory, information theory, and statistical learning theory. Read recent papers, attend conferences, contribute to open source projects. If you want to apply MLs to specific domains, develop expertise in that area. Healthcare, finance, autonomous systems, natural language processing, computer vision, each field has unique challenges and opportunities for ML application. Remember that machine learning is ultimately about solving human problems. The algorithms are tools, powerful tools, but tools nonetheless. The real impact comes from applying these tools thoughtfully to challenges that matter. Improving medical diagnosis, enhancing education, advancing scientific discovery, creating more efficient systems, or building more engaging experiences. As you continue learning, maintain both technical rigor and ethical responsibility. Machine learning systems reflect the data they're trained on and objectives they're given. Ensuring these systems are fair, beneficial, and aligned with human values is as important as making them accurate and efficient. The future of AI isn't being written only by researchers in university labs or engineers at technology companies. It's being shaped by everyone who understands these tools and applies them responsibly to real-world problems. You now have the knowledge to be part of that future. Whether you become a data scientist, a machine learning engineer, a research scientist, or simply a more informed user of AI systems, you're equipped to participate in the ongoing AI revolution. Machine learning started as an academic curiosity. Today, it powers the systems you use daily and will increasingly shape the world your children inherit. Understanding how these systems work, their capabilities and limitations, their potentials and risks, makes you better prepared for that future. The algorithms we've explored represent humanity's attempt to create artificial minds that can perceive, learn, and reason. While we haven't achieved artificial general intelligence yet, we've created powerful tools that augment human intelligence in remarkable ways. Your machine learning education continues every time you see these algorithms in action, every time you apply them to new problems, and every time you help others understand their power and responsibility. Welcome to the community of machine learning practitioners. The problems you choose to solve and the applications you build will help determine how AI shapes our collective future. The question is no longer how do machines learn, but what will you teach them?